So, for example, I could say I've got x equal to t plus 3 and y equal to t squared for t greater than or equal to, say, negative 3? Sure. So it's not the pen I thought it was. And there are lots of things you can say about this. For example, so we often talk about like how t can represent the variable time. And so you can talk about like the path of a particle that has coordinate xy at time t. So like at time -3, I know I'm taking a little bit of time to get to the surface area. And the length, we'll get there in a minute. So you're right, at time equals -3, I'm going to have x being 0 and y being 9. And then when time equals 1, x is going to be 4, and y is going to, sorry, when time equals -2, I said -3 and I wrote 0, sorry. Time equals -2, x is 1, and y is 4. And when x is 2, sorry, when t is -1, sorry, x is 2 and y is 1. When x is, sorry, when t is 0, x is 3 and y is 0. So it's kind of looking like this. And then let's plug in one more point. When t is, so they could have made a table. That would be the smart thing to do with t and x and y. Where x is just increasing, adding 3, so 0, 1, 2, 3. And y is this number squared, so 9, 4, 1, 0. So we're going to get this point here. And it's going to go like that. Now, we could actually see what the graph of this is without having the parameter t. It would be totally possible to solve this, to rewrite it as an equation in just x and y. And typically what we do is we take one of these and solve for t, usually the one that's easier, like this one. So I can say, oh, t equals x minus 3, so y equals x minus 3 squared. Which is totally the graph we have, just we don't have the whole domain. Our domain would be, well, if t is bigger than or equal to -3, then x minus 3 is bigger than or equal to -3, x is bigger than or equal to 0. So this is a way you could transform a parametric equation into a function where y is a function of x. It's not something we can always do, but it is something we can sometimes do. Well, let's ask the more interesting question. What's the length of this curve from, say, here to here? I'm not sure if we're actually able to answer this because it might be difficult, but let's set it up. So I want to find the length of this setup from t equals -3 to t equals 0. So there's two ways we can do this. So length of x equals t minus 3. Sorry, I'm trying to remember what the things are. X equals t plus 3, y equals t squared from t from -3 to 0. So the arc length formula, oh, what section of the textbook is this? That's an excellent question. This is the parametric equation section, which I think is like, that's a good question. Let me look, Morgan. In my textbook, which is a slightly older edition, this is section, I think it's chapter 9 somewhere. Maybe not. You could look in the beginning, that would probably be easier. Let's look at the beginning. In my textbook, we are looking at chapter 11. Yeah, so this is probably most closely associated with section 11.2, although it might be slightly different if you have a different version of the text. Ooh, that was smooth. Sorry. Yeah, I'm fine. Just knocking stuff over. My wife was like, are you okay? Okay. Just something was not balanced super well. Sorry, 1 second. Let me pick up the mess I made. Oh. Okay, great. Okay, so I want to find the length of this. And there's actually a third arc length, which I think I maybe slightly mentioned when we talked about arc length way back when. So typically, you find arc length is the integral of ds. And we have seen before that ds can be the square root of 1 plus dy dx squared dx, or it can be the square root of 1 plus dx dy squared dy. Well, there's a third version for parametric curves. The third version is that ds is equal to the square root of dx dt squared plus dy dt squared dt. And that's the version we're going to use here. Or at least we're going to use it to set this one up. And again, I'm going to look at it and see if it really looks like it's doable or not. So let's see. I'm going to find the arc length. T is going from -3 to 0. And we're going to get the square root of dx dt, which is 1 squared, plus dy dt, which is 2t squared dt. And yeah, we can totally integrate this if we remember how. You're like, well, yeah, great. That's helpful, James. We can totally do it if we remember how to do it. I'm being a little dumb here. Hopefully you guys can see what method of integration might make the most sense to use to integrate the square root of 1 plus 4t squared. What method? Trig is the first word. There's another thing that it's a trig substitution. Yeah, exactly. Ah, come on, pens. Okay. So exactly, we're going to let 2t equal tangent. I probably didn't pick very nice limits of integration, such as life. So 2t is going to be tangent of theta. And then take the derivative of both sides. 2 dt is going to equal secant squared theta d theta. So dt is going to be 1/2 secant squared theta. Yeah, this was going to turn out to be real awful. That's the way it goes. So let's see, plugging things in, you get the integral of the square root of 1 plus tangent squared times dt, which is 1/2 secant squared theta d theta. Okay, we've got everyone's favorite integral, the integral of secant times secant squared, which is secant cubed. This is going to be 1/2 the integral of secant cubed theta d theta from, oh, I didn't change the limits of integration. Do I want to change them? Not really. I'm just going to leave them alone. If I picked nicer numbers, I might want to change them. But t is 0, no, yeah, it's kind of terrible. So let's just finish. Let's just do it this way. So I'm going to appeal to the fact that we've already done the integral of secant cubed before. The integral of secant cubed is 1/2 of the natural log of the absolute value of secant theta plus tangent theta plus secant theta plus tangent theta. Oh, sorry, secant theta times tangent theta. It comes up every now and again. So then we should use a triangle to figure out what secant and tangent of theta are. So tangent of theta is 2t. So tangent of theta is 2t over 1. The third side is the square root of 1 plus 4t squared. So it looks like we've got 1/4 natural log of secant of theta, which is square root of 1 plus 4t squared. Plus tangent of theta, which is 2t. Plus the product of those things. The square root of 1 plus 4t squared times 2t. Whew. And then since we've got t's now, we can integrate from -3 to 0. And I don't think you need to see me plug in -3 and 0 to see how to finish this problem. Yeah, it's kind of gnarly. These problems often, these arc length problems often get kind of gross. Let's do a couple more. And then we'll talk, oh man, this eraser is going to be real gross. It'll be time for a new eraser. Sorry. Yeah, it's like brimming with black dust. It's kind of, it's time to vacuum in here. Not that I don't vacuum, but it's time to vacuum again. All right, yeah, so I was erasing. Let's look at a couple more examples of arc length with parametric curves. So let's say we have the parameterization, parametric curve, x equal to t over 1 plus t, and y equal to, what do we got here? The natural log of 1 plus t. Now I want to find the length of this when t is between 0 and 2. Right? Right. Okay, so the nice thing about these parametric lengths, the setup is always kind of the same. The length is going to be equal to the integral from 0 to 2 of the derivative, the square root of the derivative of this squared plus the derivative of this squared. So the derivative of this, we have to use the quotient rule. So it's going to be, let's do it right down here. So x prime of t is going to be bottom times derivative of the top minus the top times derivative of the bottom, all of the bottom squared. That's going to be 1 plus t minus t. So that's just 1 over 1 plus t squared. Interesting. That is interesting. Anyway, sorry, I just noticed something. And then y prime of t is going to be 1 over 1 plus t. Okay, so then we get this squared. So 1 over 1 plus t squared plus 1 over 1 plus t squared. And now what should happen, if the problem has been written in a way that you're meant to be able to do it, is you should be able to deal with this inside somehow. I'm going to notice that, well, I'm going to see that this is, so I've got 1 over 1 plus t to the 4th. And it probably makes sense to get a common denominator. So I'm going to multiply this by 1 plus t squared, 1 plus t squared. Right, this is 1 plus t squared over 1 plus t to the 4th. And I said probably, right? I'm not 100% sure. It's not always super duper clear how to actually solve these problems. In fact, I'm looking at this kind of thinking, I don't actually know. Yeah, it looks kind of gross. It definitely doesn't look like it's going to be the nice thing where something like factors out the way we want to. Let me double check and make sure I took my derivative here right, just to be 100% sure. So it was the bottom times the derivative of the top minus the top times the derivative of the bottom. No, that's definitely right. That's 1 plus t minus t, which is just 1. Okay. All right. Oh, and I've got my limits of integration. So from 0 to 2. So here's what I've got. I've got the integral from 0 to 2 of the square root of 1 plus t squared, which I could write as 1 plus 2t plus t squared over 1 plus t to the 4th. It's a good question. How are we supposed to do this one? Darn it, I hate it when it's hard to see what it is. I don't think it's a trig sub. It's a good question, right? I think, yeah. I don't believe it's a trig sub because it be a real funky trig sub. how about, let's try something else. Make 2 square root. Yeah, I was thinking about that too. Because you could totally square root the denominator. Yeah, you might. I don't think you're wrong. I'm just not. Yeah. Blah. I had another thought here, but it was too. I think what I'm going to try instead is I think instead of doing this, I'm going to actually factor out one of the 1 over 1 plus t squares. I think that's kind of the same, but let's write it like this. Let's write it as square root of 1 over 1 plus t squared times 1 over 1 plus t squared plus 1. I think I almost see it. Bring that out. Yeah, okay. Oh, we're so close. Here's what I'm kind of seeing. Oh, man. Sorry, I don't mean to be stuck with it for like, well, let's just watch him think about the problem for a minute. Okay, so one thought here is to bring this out, right? It's the integral from 0 to 2 of 1 over 1 plus t times the square root of this. Wow. Is it really a trig sub? It feels really gross to make it a trig sub. All right, I'm going to cheat. I'm going to look at the solutions. Sorry. Let's take a look here. Yeah, the problem is with the method from before is I want something squared plus 1. And I don't really have something squared plus 1 here. Whereas here, I kind of had something squared plus 1. Yeah, what I really, no, that doesn't work. Okay. The other fractions I got, I see what you're saying. Oh, yeah, okay, I get that. That's not a bad idea. But none of the ideas are bad ideas, but let me take a look at just what the solutions are so I can not lead us down the path of terribleness. Sorry, I'm looking at this problem here. Yeah, that's a tricky question. Let's see. On the solutions, it says the answers are given somewhere else. Great. Okay. So, good times. See one thing. I feel like I've let you all down here on this last day of class. Yeah, okay, I guess we can try the trig sub. So I think what's being written, although I'm not exactly 100% sure, is I think what you guys are suggesting is to write it as the square root of 1 plus t squared on top. On the bottom, the square root of 1 plus t to the fourth, which is just 1 plus t squared. Am I catching your drift? Is that what you guys are suggesting? Okay. And then, yeah, we could, my gut tells me there's another way to do this, but oh well. So we're going to let 1 plus t equal tangent theta. And then dt is going to equal secant squared theta d theta. Maybe this is the way to go. All right. So then we get the integral of the square root of 1 plus tangent squared, which is secant squared, which is secant. dt, which is secant squared, and 1 plus t squared, which is tangent squared. And it might even make, no, it doesn't really make sense. I'm just going to change it back to my original integral. Yeah, okay, this seems dicey, but okay. I think the way to do this one is to rewrite this as secant squared, secant squared is tangent squared plus 1. Yeah. So that then you can break this up into two fractions. So I'm going to write this as secant tangent squared over tangent squared, which is just secant. And then we've got secant times 1 over tangent squared. Secant over tangent squared, that's 1 over cosine over sine squared over cosine squared, which ends up being 1 over cosine times cosine squared over sine squared. Cosine cancels. You get a 1 over sine times a cosine over sine, which is a cosecant times a cotangent. So this ends up being the integral of secant theta plus cosecant theta cotangent theta, which ends up being the integral of secant, which is the natural log of the opposite value of secant theta plus tangent theta, and the integral of cosecant cotangent, which is just minus cosecant theta. From, now I have to think about our limits of integrate. Oh, we actually have to change back to t's. So tangent theta is 1 plus t. So tangent theta is 1 plus t over 1. The third side here is the square root of 1 plus t squared. So we end up getting the natural log of the opposite value of secant theta, which is the square root of 1 plus t squared, plus tangent theta, which is 1 plus t, minus cosecant theta, which is this over this. That was gross. And then we plug in from 0 to 2. So if we plug in 2, we get the natural log of the square root of 1 plus 9, so the square root of 10 plus 1 plus 2 minus the square root of 10 over 3 minus, then we plug in 0, and I bet it all goes away. Plug in 0, we get the square root of 1 plus 1. Sorry, the natural log of the square root of 2 plus 1 minus this, which is the square root of 2 over 1. Whew, that was gnarly. How fun. I mean, it is a fun problem. It feels less fun when you get stuck. Yeah. And the answer, interesting. My answer is off by, so I did make one mistake. Well, I did make one mistake. This should be a plus, so it should be minus all of this. And I do feel like, no, I've got a minus that, I've got a plus that. I feel like the solution is supposed to accidentally have a minus, have a plus sign where there's supposed to have a minus sign. So it looks right. Gnarly. And I feel like, yeah, that must be I don't know how else you're getting that. So yeah, that looks pretty interesting. Yeah, I guess there isn't any other way to do it. I just felt like there would be. Sometimes things simplify nicely. Sometimes you're stuck with a terrible trig substitution. I was hopeful this one would be nice, but it wasn't. I don't think anyway. I guess it doesn't matter if there's a nice way to do it. We should do it the way that's the easiest and most direct for us to do it. I mean, if we see a trig sub, it's not worth spending the time messing around trying to make the algebra work. Because one, the algebra might not actually ever work out nice. And two, we should do what we can do. So let's look at the next one here. And let's look at x of t. Oh, and then we'll do some surface area as well. X of t equal to e to the t sine of t. And y of t is e to the t cosine of t, I believe. Yes. This one, I think, is going to be quite a bit nicer. And then t is between 0 and pi. So again, the setup is always going to be the same. We're going to say that the length is equal to the integral from 0 to pi of the square root of the derivative of that squared plus the derivative of the other thing. All right, it's a bit lazy they're writing out. Okay, so this one might not be as nice as I hoped it was going to be. The length ones are like never nice or rarely nice. So the derivative here, we have to use the product rule. It's going to be e to the t times sine of t plus e to the t times cosine of t. And the derivative of y prime, or the derivative of y, is going to be e to the t cosine of t minus e to the t times sine of t. Okay. I can factor out e to the t from each of these. So when I square this, it's going to be a bit of a mess. What a shock. So when we square this out, we get three terms. We get this squared plus the middle thing plus this squared. And here we get this squared plus the middle thing plus this. Now, here's what I'm seeing. So let me write it actually this way to make it a little bit easier. I'm going to say this is a plus b, and this is, sure, or b plus a if you like, and this is b minus a. So I've got b plus a squared plus b minus a squared. And if we square this out, we're going to get b squared plus 2ab plus a squared plus b squared minus 2ab plus a squared. The 2ab's will cancel out. Oh, son of a gun. Oh, oh man, don't get old. It turned my neck and it just like, that does not feel good. I'm not dying, but it's like, oh man, you know when you ever turn your head too fast, you're just like, wow, oh, geez, that was a great last day of class. Okay, so here's what's gonna happen, right? We're gonna get this thing squared twice and this thing squared twice. So what I'm gonna get is 2 times a squared, which is e to the 2t sine squared of t. And I'm going to get plus 2b squared, which is going to be, well, this thing squared, e to the t squared is e to the 2t. And cosine squared is cosine squared. Are there questions about what I did before I move on to the next step? I was really just trying to make my life easier by not having to write out all of this squared plus all of this squared. Okay, well now this is actually not terrible at all. So we can factor out a 2e to the t. And I think everybody knows that sine squared of t plus cosine squared of t is what? Right. And so then we're just left with the square root of 2e to the 2t, sorry. So this is going to be the integral from 0 to pi of the square root of 2, and the square root of e to the 2t is just e to the t, right? Because e to the 2t is e to the t squared. So this one actually turned out to not suck. So this is going to be the square root of 2. Integral of e to the t is e to the t from 0 to pi. So we get the square root of 2 times e to the pi minus e to the 0. Cool. All right, let's do one more, and then we will, hopefully I'll make it through to one more, and then we'll do some surface area ones. And then if there are other things you guys really are dying to see, please let me know. Maybe best choice of words. So look at this last one I have to look at. I've got x equal to 4 times the square root of t. If there's any specific ones from the Morris homework as well, I can also look at that. X equal to 4 square root of t, and sorry, where'd you go? And y equal to t squared plus 1 over 2t. For the person asking about moments, do you just mean like back when we did it way back when, or are you talking about moments with parametric equations? You can let me know. So again, right, the process, although the process is ugly for this arc length one, it's still the same process every time, right? You're still doing the same darn thing. You're finding the arc length is the integral. Oh, sorry, we're given here that t is between 1/4 and 1. So it's just the integral of the square root of your derivative squared plus your derivative squared. So the derivative of this is going to be, let's see, I've got 4 times t to the 1/2. That's going to be 4 times 1/2 t to the negative 1/2, or 2 times t to the negative 1/2. And the derivative here is going to be 2t, and let's see, this is 1/2 t to the negative first, so its derivative is going to be minus 1/2 t to the negative second. And this, to me, is looking kind of like the ones we used to see, where you squared things out and then you're getting a minus 1/2 to add to your 1 or whatever. So it turned out to be the opposite sign. Maybe. We'll see. So I'm going to square this. I'm going to square this. Not too hopeful here. So let's see what we get. We get the integral from 1/4 to 1 of the square root of, it's going to be 4t to the negative 1. Multiplying this out, I'm going to get a 4t squared. Then twice the terms multiplied together, so I'm going to get, oh, it's going to be negative, so it's going to be minus a t. This times this is going to be, let's see, 2 times 1/2 is 1, and then t to the first and t to the negative first is t to the negative first. It's going to be twice that. So I'm going to get 2t to the negative first. And I am stoked about that, because this thing here, when I add this to this middle term, it's just going to flip its sign from negative to positive. So I'm pretty sure it's going to work out the way I hoped it was going to. And then this last part here is going to be plus 1/4 t to the negative 1/4. I just want to remind everybody, right, that this part here is this. That's what all this is up here. Okay, well now look what's going to happen. I'm going to add 4t to the negative 1 to negative 2t to the negative 1, and I'm going to get positive 2t to the negative 1. This is going to be the integral from 1/4 to 1 of the square root of 4t squared plus 2t to the negative 1 plus 1/4 t to the negative 1/4. And since this thing factors this way, this thing, where the sign in the middle is just changed, factors as this, except it's going to be a plus instead of a minus. This is going to be exactly the integral from 1/4 to 1 of the square root of 2t minus 1, sorry, plus 1/2 t to the negative second squared. And now everything's going to work out pretty great. So, sure, we can erase this. So I'm going to integrate, well, I'm going to simplify this, and then we'll have the integral of 2t plus 1/2 t to the minus second. And then we're going to anti-differentiate that, and we're going to get t squared minus 1/2 t to the minus first, which is exactly the function we started with, is it? He says. No, not exactly. It's kind of the function we started with. It's the y part of the function we started with, I guess. Evaluated between 1/4 and 1. So then we can plug, except it's the y part, except the sign has changed. So you plug in 1, you get 1 minus 1/2, minus you plug in 1/4, you get 1/4 minus, 1/16 minus 1/2 times 1/4 to the negative 1 is 4, so it's minus 1/2 times 4, or minus 2. And then you can simplify this. It simplifies to, I think, 39/16. So it's 16/16 minus 8/16 minus 1/16 plus 32/16. Yeah, that's 39/16. Okay. So let's do some surface area, and then I'll see if I can muster the will to talk about moments some more. All right, let's see here. So where did we go? I got 2 surface area problems to throw at you. So the nice thing about surface area is it's really just arc length, an extra piece. So let's look at this one. Find the surface area when each curve is revolved around the x-axis. So we're going around the x-axis. I'm going to have to be extra careful here. Yeah, okay. Yeah, all right. So we've got we've got x equal to cosine cubed t. We've got y equal to sine cubed t. And we have t between 0 and pi over 2. Okay, this is actually kind of interesting. So we've got some curve. I don't know really what it looks like. It looks, I mean, I know it's got the point 1, 0, because if you plug in 0, you get x is 1, y is 0. And you also know we get the point 0, 1. Because, and sorry, I should say t is between 0 and pi over 2. But this I think is going to bring up an interesting point here. So when t is pi over 2, we get x is 0 and y is 1. It doesn't look really like a quarter of a circle, but that's my picture I'm going to draw. And then we're going to revolve this around the x-axis. So typically when we revolve something around an axis like this, the surface area of my rubber band is 2 pi times the radius times the ds. Right, the radius is that part, the ds is that part. So, just doing all the things. Didn't get pen on the ground, which is good. Okay, so I'm thinking of like this part here, and that's my little ds, and we're revolving it like that. All right, so the ds is obviously the same thing it was with the arc length. Maybe not obviously. Sorry. I don't mean to say things are obvious if they're not. Just it's like ds is always going to be the arc length thing. It's the square root of whatever. So ds is still square root of dx dt squared plus dy dt squared dt. Okay, can someone tell me in this particular problem what my radius is if we're going around the x-axis? Right, my radius is y, which in this case is sine cubed of t. So when you're doing a parametric surface area equation, you have to think about which axis you're going around. Your radius is the other variable. And then you have to plug in the function that the other variable is actually equal to for your radius. So here to find the surface area, it's going to be the integral from 0 to pi over 2 of your 2 pi times y, which is sine cubed of t, times your ds, which is the square root of gnarliness. Let's see. So the derivative of cosine cubed is going to be 3 cosine squared of t times negative sine of t. And the derivative of sine cubed of t is going to be 3 sine squared of t times cosine of t. I'm not feeling good about this. So let's see, what do we got here? I can factor out a cosine and a sine and a 3. So I'm left with the integral from 0 to pi over 2 of 2 pi times sine cubed of t times the square root of 3 times cosine of t times sine of t times, I'm left with a negative cosine and a positive sine. Seems very bad. What am I missing here? I don't know. Yeah, I am. It is that right? Okay. What could we do? Yeah, I don't know. That seems real gross. Let me make sure I didn't make a mistake somewhere. Derivative of this is definitely 3 cosine squared times 0 cosine. No, that's right. 3 sine squared. All right, yeah. You factor out the cosine and the sine, which is all you can really do. Yeah, I don't know. So, I mean, if we were going around the x-axis, which means and then like, so this part, I don't think this problem really is making a difference that much if you're going on the x or the y. If we're going on the y-axis, we'd be multiplying by cosine cubed here, which wouldn't really change much, at least from my perspective at the moment. I mean, I guess there's probably some, there's some trig identity. Yeah. What is it? Oh, what's that dumb identity? There's an identity here. Shouldn't sine t be squared in the parentheses? Here? No, because so from each of these, so from here I factored a cosine and a sine. Oh, it should actually be a cosine. Oh, I did it. I see what I did. I factored out a cosine times sine from here, and I'm left with a 3 sine, or just a sine, because I factored out the 3 as well. And then I factored out a cosine times sine and a 3 from here, and I'm left with a negative cosine. So I'm pretty sure that's correct. Unless I'm really just totally blowing today. But yeah, there's clearly something to do here that I am not seeing. I don't know. And I don't really see, that's not true. Let me look. There is a trig identity I think we're supposed to be using. Where are you, trig identity? It's the gross, yeah, you are not my favorite. Oh, that seems terrible. I really don't believe that's it. There is a trig identity for. I don't know. There isn't even a trig identity for that. Yeah, it's just. Well, sorry to lead you guys down the paths of so many problems that I am certainly struggling to complete. Yeah, this problem is. I don't see it. Someone else sees it. All ears. I mean, okay, I guess we could try a U sub. I don't know what you're letting U equal, though. I feel bad giving up on the problem, but I think we might have to give up on this problem. Yeah, I'm going to give up on the problem. I'm going to try to give up on the problem. Let's look at the different surface area problem. Look at this next. I'm going to scope out this next one. This next one looks a little more reasonable. Maybe we should have started with this one. So here's another one. So it's x of t is 2 plus cosine of t. I have a feeling this one's going to be much easier. And y is 1 plus sine of t. Yeah, this is almost too easy, but still reasonable. So we're going around the x-axis. And we are going from between 0 to 2 pi. And we're asking for the surface area. So again, surface area is the integral of 2 pi r ds. That's going to be the integral from 0 to 2 pi of, 2 pi times my radius, which is my y value, which is the y function, so 1 plus sine of t, times the square root of, I'm pretty sure it's going to be 1 here. That's right, the derivative of x is negative sine. It would be negative sine of t squared. And the derivative of y is cosine of t. It would be cosine of t squared. This one's much more straightforward. This is going to be the 2 pi times the integral from 0 to 2 pi of 1 plus sine of t. And this is just 1, right? It's the square root of the sine squared plus cosine squared. So then we get, integrate this, you get t plus integrate this, you get negative cosine of t. Times 2 pi from 0 to 2 pi. So we plug in 2 pi, and we get 2 pi times 2 pi minus cosine of 2 pi is 1, minus you plug in 0, and you get 2 pi times 0 minus 1. And that's going to be 2 pi times 2 pi, so 4 pi squared minus 2 pi plus 2 pi. Interesting, or maybe interesting question. If we had gone around the x-axis instead, around the y-axis instead. So if you're around the y-axis, the ds part still stays the same. So that's just 1. So on the y-axis, we'd be getting the integral from 0 to 2 pi of 2 plus cosine of t dt times the 2 pi out in front. So almost the same. Oh my God, Mindy, thank you so much. It was killing me. I think you're right. And I think that might have been what Mariah was also alluding to, but I was missing it. Thank God. It was gonna kill me. Yeah, I totally forgot to square my derivatives. Good point. Whew. Okay, so let's continue on. I'm glad we took a break so that we could not just go crazy trying to figure it out. Okay, so this should hopefully work out better now. Because I think now we can factor stuff out and not be so terrible. So here's what we're going to get. I've got the integral from 0 to 2 pi. I hope everybody caught that, right? I'm glad Mindy caught that we have to square it, right? It's the square root of dx dt squared plus dy dt squared. And I totally forgot to square them. So let's see. I've got sine cubed of t. And then here I'm going to have the square root of, so I'm going to square these. I'm going to get a 9 and a factor out the 9. And then we get cosine to the 4th times sine squared. Oh man, thank you so much. I was really about to not be happy with how my life is going. Okay, so that's what we've got. We've got 9 times cosine to the 4th times sine squared plus sine to the 4th times cosine squared. Excellent. And now we can totally factor out a cosine squared and a sine squared from each of them. It's a good point. I should have known that we didn't have the right thing, because you shouldn't have something being able to be negative, because it should always get squared. So, excellent point. So we're getting, let's see, 2 pi integral from 0 to 2. Oh, was it 0 to 2 pi? I think it was 0 to pi over 2. Yeah, it was 0 to pi over 2. Square root of 9 is 3. And then I'm factoring out a cosine squared times a sine squared. And yes, this is going to work out so much better. Because then we're left with a cosine squared plus a sine squared. Thank goodness. Which is 1. Square root of that is cosine, square root of that is sine. So we can write this as the integral of 6 pi, right? 2 pi times 3, 0 to pi over 2, of sine cubed of t, square root of cosine, square root is cosine, square root of sine, square root is sine. And now this is one of those powers of sines and cosines problem that we can totally do. So let's rewrite this. This is 6 pi times the integral from 0 to pi over 2 of sine to the 4th times cosine. So let me ask everybody, are we going to let u equal sine or u equal cosine? So it's a good question. So you always want to pick u to be the one that after you deal with du, there's an even number of the other thing left over. So if you pick u equal to cosine, your du is sine. You pull out one sine, and there's a sine cubed left over. I don't want an odd number of the not u choice left over. So instead, if we pick u equal to sine, du is cosine. We immediately take care of it. There's 0, which is an even number of cosines left over. So we're safe. Or sorry, yeah, okay, yeah. So yes, we're going to let u equal sine. Basically, you want there to be a trig identity left over. So u equals sine of t, du is positive cosine of t. This is going to be pretty straightforward. It's going to be, he says after the problem was like almost impossible for him. It's going to be pretty straightforward. It's going to be pretty straightforward at this point. So this is going to be u to the 4th times du. And something, I don't know, actually it's going to be fine. If t is 0, sine of 0 is 0. If t is pi over 2, sine of pi over 2 is 1. So we end up with 6 pi times u to the 5th over 5 from 0 to 1, which is going to be 6 pi times 1/5. Thank you all for your help. I appreciate it. I'll be going mad later on. Mad, I tell you. Okay. I feel like that's maybe enough of all this gnarliness. Actually, let me take a quick gaze and see if there's any problems that Morris give you guys that look particularly interesting. So there's actually, so that sine cube, cosine cube problem, that's very similar to Morris's problem number 7 on PS9. Yeah, I don't think there's anything on there that's too terrible looking. I think you guys will be all right. So someone asked for some moments and center of mass stuff, which let me grab some problems here. That's never been my forte, but I can certainly address. Let's see, moments and center of mass. Where'd you go? Where did you go? Oh, there we go. Oh, my eye has been twitching like for today and yesterday. It's just like my left eyelid is trying to close, and I really don't want you to. Oh my God, it's really like, sorry. I know you guys don't really need to know this. Oh, it's just, where'd you go? I can't find the thing I'm trying to find. You know what? There's always the book. Let's find some center of mass questions in the book. Let me clarify for the person who asked this question, or for anybody. Are you looking for problems that have constant density or variable density? Both. Okay. Fine. Let's see, I guess we're in chapter 7. Sure. Page 400. So let's take a look at some example problems here. Plates with constant. So let's do one with constant density. So these are all about finding the center of mass. Sure. All right, let's look at this one. The region bounded by the parabolas y equal to 2x squared minus 4x and y equal to 2x minus 2x squared. Okay, yeah, variable is harder for sure. Let's look at the constant. Let's look at the constant density one just so we can kind of get our bearings, and then we'll do a variable one. So I want to find the center of mass for the region with constant density bounded by the following parabolas. Did I pick an odd problem? Am I smart enough? Nope, I didn't. Oh well, it's too late. Y equal to 2x squared minus 4x, and y equal to 2x minus x squared. Okay. When you're talking center of mass for a constant density plate, shape, whatever, you're really just talking centroid. Are you talking about the geometric center? Because it's not like it's heavier in one part than another. Let's draw a picture here so I can factor this. This is 2x times x minus 2. This is x times 2 minus x. So this parabola, which opens upwards, has intercepts at 0 and 2. Looks kind of like if x is 1, negative 2, sure. And this other parabola looks like it opens downwards. It's also got intercepts at 0 and 2. How convenient. Looks kind of like this. So I'm looking at this region here. Okay, here's something that's nice to know about this. We're still going to do the work, but I'm going to tell everybody right now that since both of these parabolas have their vertex at x equals 1, right, they both are symmetric about the vertical line x equals 1, I am 100% positive that the x coordinate of the center of mass, or the centroid, is x equal to 1. And it is perfectly valid to use symmetry of a region to say that the centroid is located on the center line of that region. So I already know, although I'm still going to show the work, that x bar, which is the moment around the y-axis divided by the total mass, absolutely positive it's going to be 1 because of symmetry. Okay. So to find the things, we need to find, so to find x bar, we need the moment around the y-axis divided by the mass. To find y bar, we need the moment around the x-axis divided by the mass. Okay. And I'll remind everybody that for this, right, the moment around the x-axis, oh gosh, sorry, I remember how the formulas work. Let's do the moment around the y-axis first. So this would be, yeah, let's go to the other side here. So the mass of the region is just the area of the region times the density. If I call this top function f and this bottom function g, then the area is the integral of f minus g. And so the mass is the area times the density. The moment is the lever arm length times the mass. So if you take some region, let's use a garbage pen over here. You take some region here. It is x away from the y-axis. The moment of that region is x times the mass of that region. The mass of that region is the height of that rectangle times the base of the rectangle. So the moment for that part right there is going to be the mass of the rectangle there's the mass of that one rectangle, it's f of x minus g of x, the height times the base, which is dx, times the lever arm, which is x, times the density. But then we want all of the moment, right? We don't want the moment for just this rectangle, we want the moment for all the rectangles. So we iterate from 0 to 2. And the point I want to make is that these densities cancel out and they're constant. So we typically just calculate this over this. So this bottom part here, the integral from 0 to 2 of f of x minus g of x is going to be, let's see, f of x is, sorry, this is f of x, this is g of x. So f of x is 2x minus x squared. G of x is 2x squared minus 4x. So let's see, simplifying this, we're going to get, let's see, 2x plus 4x is 6x, and negative x squared minus 2x squared is minus 3x squared. Someone thought hard about making this problem turn out nice. So we're going to integrate this, we're going to get 6x squared over 2 minus 3x cubed over 3 from 0 to 2. Plug in 2, you're going to get 12 minus 8, which is 4. And that is the area of the region, and we don't have the density, it's fine. Okay, let's find the moment around the y-axis. Now, here's the thing. I already know that x bar should be 1. So I'm pretty sure the moment of around the y-axis should be 4. So the moment around the y-axis is going to be, and again, here we're kind of abusing notation, right? Really, the moment around the y-axis is the density times the thing I'm finding, but people just kind of let it slide. So the integral from 0 to 2 of x times f of x minus g of x. Now, I could write x times all of this, but we already found that f of x minus g of x was equal to this. So I can just do x times that. So I'm going to get the integral from 0 to 2 of 6x squared minus 3x cubed. I'm a little worried the numbers aren't going to come out right, but it's okay. I mean, it's not okay. It should come out right. So I'm going to get 6x cubed over 3, which is 2x cubed, minus 3x to the 4th over 4. Oh, I think it's going to be okay. From 0 to 2. Plug in 2, and you get 2 times 8, which is 16, minus you plug in 2, 2 to the 4th is 16. 16 over 4 is 4. 3 times 4 is 12. So yeah, our x bar is 4 over 4. Now, what I want to say is if someone asked you this question on a test, they've probably thought about it enough that they kind of expect you to use the symmetry. So I think it's usually perfectly fine to say, like, especially for like a semicircle, if someone says you got a semicircle and you want to find the center of mass, the center of mass is definitely located somewhere on the line that cuts that semicircle directly down, assuming it's a constant mass, a constant density, right? It's somewhere like there. And you should use the symmetry of your shape to say that I at least know one of the coordinates is easy to find. On the other hand, the moment we're on the x-axis, to calculate y bar is going to be a little more challenging. So the denominator is still the same, right? It's going to be 4. But on top, the problem is we can't really draw a horizontal line and say it's y away from the x-axis. What we have to do is we have to do the thing where we say all this mass is located, or we think of it all being like right in the middle. And we say that that middle point is some y value away from the x-axis. And that y value is actually just the average of these two functions. So our moment on the x-axis is the following. The density, which cancels out, and then it's the integral from 0 to 2 of the area of your region, or the mass of your region without the density, which is still the same as it ever was. It's still your f of x minus g of x. I'm going to run out of room here. But then the average of these two functions, which is how far away all this mass is thought to be from the axis, is, well, the average of two things, you add them together, you divide by 2. So it's f plus g divided by 2. And we usually end up writing this as the integral of 1/2 f of x squared minus g of x squared. Right, because when you do f minus g times f plus g, you get f squared minus g squared. All right, so let's calculate mx. Sure, I've got room up here. Now, I will say, looking at the shape, my guess is it's going to be negative because it looks like there's more area below than above the x-axis. Let's find mx. So mx is the integral, 1/2 integral of f squared minus g squared, which is going to be 1/2 the integral of, here's my f, here's my g. It's going to be 1/2 of 2x minus x squared squared minus 2x squared minus 4x squared. It's usually kind of gnarly. So we have to multiply it out, which is nobody's idea of a good time. Oh, wow. Do be careful, right? It is f squared minus g squared, not f minus g quantity squared, which I definitely have seen people make that mistake before. We get 1/2 times the integral from 0 to 2. This squared, which is 4x squared minus 2x times x squared is negative 2x cubed, so negative 4x cubed plus x to the 4th minus all of 4x to the 4th minus 16x cubed. Good Lord, plus 16x squared. Put it all together. Sure. Get 1/2 times the integral from 0 to 2. 4x squared minus 16x squared is negative 12x squared. Negative 4x cubed plus 16x cubed is 12x cubed. And x to the 4th minus 4x to the 4th is minus 3x to the 4th. I lost the cube there. And you could, no, I don't want to. Okay, so we integrate. Oh my goodness. These moment problems are always feel like super long because there's just so much arithmetic to do usually, which is why you should take whatever shortcuts you can. So you get 1/2, integrate this, I get negative 12x cubed over 3, so negative 4x cubed. Integrate this, you get 12x to the 4th over 4, or 3x to the 4th. And then integrate this, and you get negative 3x to the 5th over 5. We were so close to not having to deal with any fragments. From 0 to 2. Also, notice I haven't been plugging in the zeros because I know that everything's extra power, but you be careful, right? For other types of functions, you plug in 0, you don't always get 0. All right, let's see what we got here. So I've got -4 times 8 plus 3 times 2 to the 4th, which is 48, minus 3 times 2 to the 5th over 5. 3 times 2 to the 5th is 3 times 32, which is 96 over 5. And that's a number. Okay, fine. It's 16 is 80 over 5. So I've got 80 over 5 minus 96 over 5. So I've got 1/2 of -16 over 5, which is -8 over 5. That's your moment. And so then your y bar coordinate is your moment around the x-axis divided by your mass, which is -8/5 over 4, which is -2/5. Holy smokes. Okay. Let's talk about a varying density one in these last 7-ish minutes. Let me look at the problems here before I pick one that's ugly. Sure, we'll go with something that seems like it might not be awful. So the only difference between what I just did and what I'm about to do is that now the density also has to be part of the integral because it's variable. So let's look at this problem. Center of mass of a thin plate covering the region between the x-axis and the curve y equal to 2 over x squared. Y equal to 2 over x squared between 1 and 2. So there's the curve. So I'm looking at this plate. That curve is y equal to 2 over x squared. And the density at x, and sometimes the density can depend on x and y, but most of these just depend on x. The density is given by x squared, which hopefully will make this not terrible. All right, so we have to find 3 things. We have to find the mass, which is the integral of the function. So this one's also nice because the bottom function is 0. So the mass is just the integral of this function times the density. The moment around the y-axis is going to be the mass integral with another x in it. Right? It's the lever arm times the mass. Right? This is ordinary reading for the mass. And then finally, the moment around the x-axis, well, again, it's your lever arm, but again, so lever arm around the y-axis, right? If you're thinking about this vertical strip around the y-axis, the lever arm has a length of x. Around the x-axis, the lever arm has a length that is 1/2 of the height of the function. Or really, it's the average of the height, but since the bottom one's 0, it's 1/2 height. So the moment around the x-axis is going to be 1, from 1 to 2, of 1/2 of my function. And that's my lever arm there, times the same thing here. Okay, so this is not too incredibly gross. So the mass here is going to be the integral from 1 to 2 of 2, which is just going to be 2, because you're going to get 2x, and plug in 2 and plug in 1, you're going to get 4 minus 2, which is 2. Okay. This one's going to be the integral from 1 to 2 of 2x, right, because this is x and this is 2. So that's going to be x squared from 1 to 2, which is going to be 3. And finally, this one's going to be a little bit more work. Let's see. 2 cancels, 2 cancels. So you get the integral from 1 to 2 of 2 times x to the negative 2. So the integral of that is 2x to the negative 1 over negative 1, 1 to 2, which is negative 2 over x from 1 to 2. So you get negative 2 over 2. Interesting. Minus, okay, negative 2 over 1. I was worried it was going to be negative for a second, which definitely seems wrong. But it's not. It's negative 1 plus 2, which is 1. So finally, the x bar coordinate is my over m, which is 3 over 2. And the y bar coordinate is mx over m, which is 1 over 2. So my center of mass is 3/2, 1/2, right there, approximately. So really the only difference between the variable density ones and the constant density ones is that for the variable density, the density sorry, I just lost my, brain. The density has to actually be in your integral. It's not just, for the moment, the lever arm times the function. It's just the lever arm times the function times the density. Same deal here, lever arm, function, density. Or for the mass, it's the function times the density. But that's the only real difference between the variable density ones and the not variable density ones.